The objective of this video is to derive expressions for torque and forces acting on the rotor of a P ±1 pole pair bearingless motor with a cylindrical rotor. Our objective is to come up with the linear force model of a bearingless motor. And the linear force model is this expression here, which says that our force vector is equal to a complex coefficient, Kf, times our suspension current space vector. So in a previous video, we've been talking about a current space vector of I, which was our motor currents. Now we're talking about the space vector Is, which are the currents in our three-phase suspension winding. So our force model is this complex coefficient Kf times our suspension current space vector plus a coefficient K delta times this vector delta. And the vector delta is the displacement of our rotor in the x and y direction. Our focus in this video is on the first term. And along the way, we're going to develop an expression for our torque on the motor, which corresponds to the traditionally used torque sizing law. So this is kind of a gut check, a reality check that the derivation we're doing makes sense. And so this whole force model, it's a linearized model, so there's some error here. And it pretends that the two phenomena are decoupled. It pretends that rotor displacement is decoupled from control currents. So to better illustrate what I'm talking about here, I've drawn a rotor centered in the air gap. And if we pull this rotor in some direction, the direction that we're pulling it, the direction that it moves, is delta, the delta vector. We can create a force on this rotor, and that force is this F vector here. And we can model the force, the electromagnetic forces on this, as being due to our currents and being due to any displacement. And so we derive these phenomena independently. We consider the forces that are due to current for when our rotor is centered. When our rotor is centered, we have no forces on it if there's no current. But if we flow current in the suspension winding, we create forces. And so what we're going to do in this video is derive the conditions on that suspension winding, how we design that suspension winding in order to create forces. And the end result is these conditions as well as what the force expressions end up being. Again, we have two windings that are sharing slot space in our stator. So these are two separate windings. Each winding is three phases and is controlled with a separate space vector, is controlled with its own set of currents. So the first winding is the motor winding, and we denote the currents in that winding using the current space vector of I. And this winding is designed to have P pole pairs. And the second winding is our suspension winding. This is what we use to create magnetic levitation forces. And this also carries three-phase currents, and we denote those three-phase currents using the space vector I, and this should be IS. And this winding, I'm cheating here a little bit, I'm giving you the answer right away. This winding is going to have P subscript S pole pairs, and it's going to be plus or minus one of the motor pole pairs. That is the condition that we're going to derive, is that your suspension winding has to have plus or minus one pole pairs compared to the motor winding. And our agenda is that we will use the Maxwell stress tensor to derive the forces and torques. And so this is the Maxwell stress tensor. This should be familiar to you from a previous video. And in order to evaluate the stress tensor components, in order to evaluate our normal pressure density and our tangential pressure density, we need to know what the normal and tangential field components are. And we'll rely on our previous video that reviewed the fields in an electric machine due to the magnetization source, such as permanent magnets, as well as due to windings. And we'll now summarize those results here. And so we have fields in both the normal and tangential direction. In the normal direction, we have a field component due to our magnetizing field, so our permanent magnets or our field coil. And then we have a component that's due to our stator winding. And the stator winding component we relate back to this current space vector, or we can express it in terms of the linear current, the electric loading of the machine. And remember, we got two windings. One winding for motor, which has P pole pairs, and one winding for suspension forces, which has PS pole pairs. So depending on which winding we're talking about, N is either equal to P or PS. In the tangential direction, we have only fields that are due to our winding. So again, we've got two windings, so N is either equal to P or PS, depending on the winding we're talking about. And this field is simply related back to our linear current density as shown. Okay, the stage is set. We are now ready to commence with torque and force calculations. Again, we'll be using the Maxwell stress tensor and then these fields that I've indicated down here. To calculate torque, we integrate the tangential force density, that is the pressure that's acting on a radial surface but in the tangential direction, over the entire surface of our rotor. So we treat our rotor like a cylinder and we evaluate this surface integral in order to find the torque acting on it. And torque, remember, is force at a distance. There's a lever arm, that's why we have this R right here. We've got L pulled out. Technically, we would be integrating over the whole axial length of our machine, but fields don't vary in the axial direction, or at least we're assuming that they do not, so this comes outside the integral, and we're left with an integral from 0 to 2 pi of our tangential force density as a function of alpha, and then this R d alpha is our area integral. We evaluate this by plugging in our expression for sigma f tan, which depends on 1 over mu naught times our normal force and our tangential, normal field and our tangential field. And so you can see that I've only indicated a single winding's fields, but I've kept it general. I've kept it with an N pole pair winding, so this could be interpreted as either the suspension or the torque winding. And we'll see that only the torque winding contributes to torque. So looking at this first term, what I've underlined in green, I've worked the math down below. I've used a trig identity to expand this into two sine terms. And we can see that one of the sine terms has alpha with a period of p plus n, with a frequency of p plus n. And the other sine term has alpha with a multiplier of p minus n. And in this winding, both p and n have to be greater than 0, or in this machine. So p is greater than 0, n is greater than 0. We know this because p is the number of pole pairs of the motor. You can't have a 0 pole pair motor or a negative pole pair motor. And n is the number of pole pairs of the winding. And the same thing goes. It has to be a positive integer. We know that if you integrate a sine over an integer multiple of its period, it's just 0. So it's impossible for this to produce any torque. The integral of sine of some integer times alpha from 0 to 2 pi is always going to be 0. So the only term here that can produce torque is this term, and it will only work if p equals n. So that's this first term. Now let's check what happens with our second set of terms over here. And in this set of terms, we see that this is always going to be 0, and so is this. So the only way that we can produce torque is if we meet this condition right here. So we need to have p equals n, or maybe I should write this the other way. We need to have our number of winding pole pairs equal to our number of motor pole pairs in order to create torque. And we already know this. This is just a sanity check, and it's preparing us for the more difficult force calculations. And we're now ready to complete our torque calculation. And so what we see is that we get this expression for torque, which is 2 times the volume of our rotor times b delta hat times a hat divided by 2, so our magnetic and electric loading divided by 2, and then times the sine of alpha w minus theta. So remember that theta is the angle that our rotor's direct axis is located at any given time. So that is to say, theta is constantly increasing. As the rotor rotates, theta changes. So to produce a constant torque value, we need to have the angle of our current space vector be equal to theta, and then we can have some additional phase in there. So if it's strictly equal to theta, the sine of theta minus theta equals 0. We have no torque. So we need to add a phase angle to our three-phase currents. And let's summarize our findings. So we have our torque expression written as 2 times the volume of our rotor times this quantity here. And so I've written this with these angled brackets to indicate that this is the average of our tangential force density. It turns out that this is indeed true if you calculate the average of the tangential force density. So that is, we go back to this expression up here and we integrate it over 2 pi and then divide by 2 pi. This is a definition of the average of a quantity. We get this expression right here, which indeed matches this. So the average of our shear stress times the volume of our rotor times 2 is the torque that appears on our rotor. And you can see that then our shear stress, we've assumed that we have our current space vector with this definition. Our shear stress has the sign of phi in it. And so we can depict what's going on in the figure on the right here. I've drawn a 2-pole machine. I haven't drawn the stator, but I drew the equivalent surface current density in the inner bore of the stator. And in this machine, we've got our north pole facing over here. So here's our direct axis, and it's located at theta radians off the x-axis. And then phi radians past that is our current space vector, which determines where our equivalent surface current density is located. That determines the angle alpha w. Because remember, alpha w is, we decided, is going to be equal to theta plus phi. And so this argument that we produce maximum torque when the sine of phi is 1 means that that would correspond to phi equals 90 degrees. Or in other words, our equivalent current density is rotated past the rotor by 90 degrees, and it's in quadrature. So that would mean that our current alpha w would be located right here. And we'd have current like this. And if you go back and you compare this against the Lorentz force law, you can see that this indeed is going to maximize your torque because you've got the maximum amount of field cutting this conductor over here and this conductor over here. Okay, so all this is building up our physical intuition and kind of a sanity check on what we're about to do for bearingless motors. This matches the machine design sizing video that we present in the machine design course. And let's take this a little bit further and talk about our current space vector for torque. So we can break our space vector up in terms of d and q axis currents in the conventional way. And that is that we have these d and q axis currents that are rotated by our rotor angle. And the argument of these currents is phi, which is the arctan of this quantity. I just forgot the arctan here. So the arctangent of IQ divided by ID gives you the angle of this component right here. And that determines this angle right here. So we can break this up into D and Q axis currents in the conventional way that we talk about in our motor drives class. And we can see that relation that Q axis current produces torque and D axis current does not holds up here. And keep in mind that all of this is for a non-salient pole machine. This assumes a cylindrical rotor. Okay, great. We've just proved vector control operation or field-oriented control operation of a non-salient pole machine. We see that IQ produces torque, ID does not produce torque, and we can maximize our torque per ampere by controlling currents only based on IQ, by only controlling the Q-axis component and setting the D-axis component to 0. I want to draw 2 key observations from this. The first is that since PS is not equal to P, since our suspension pole pairs are not the same as our motor pole pairs, in this machine, which only contains the fundamental harmonics, the suspension winding does not create any torque. So you need your fields, your air gap fields must have the same harmonics in order to create torque. the suspension winding has a different harmonic than the magnetizing winding does, than the magnetizing field does, and so therefore it is unable to create any torque. And the final observation, which is something that we're all already familiar with, but that our stator currents are going to be sinusoidal. Remember, our stator space vector is rotating with the rotor's direct axis, which means that our three-phase currents are going to be sinusoidal, and they're going to have a frequency of theta dot, which is just equal to our synchronous frequency. This should not be a surprise. Now we're going to produce the analogous derivation for suspension forces next. So we followed a pretty specific path here. We went back to our Maxwell stress tensor, and we looked at the tangential component because that produces torque, and we plugged in our fields, and then we integrated that over the rotor's surface in order to find torque. And from there on out, we related this back to our current space vector that establishes our electric loading to make observations about the different current components in that space vector. We will now do the same thing, but for suspension forces. And so we'll start by calculating force in the x direction, and we're going to do this by again evaluating the forces on the surface of our rotor over the rotor's surface area. So we're going to integrate the pressures on the surface of the rotor over the rotor's surface area. We want to differentiate this in terms of x and y direction forces, so we're going to take the dot product of our stress vector with the x direction. So what does that look like? If we're going back up here, and we've got this component in the radial direction, this in the tangential direction. So we'll write that out, and then we'll talk about how to do the dot product. So we're drawing a vector to a location on the rotor surface that we're integrating at. And at this location, we will depict the unit vector for our radial and our tangential components. And what we want to do is evaluate the dot product of these components so we can plug it back into this expression up here. And so r hat dotted with x hat is equal to cosine alpha. Phi hat dotted with x hat is equal to the negative sine of alpha. Again, we're doing that to evaluate these dot products right here. And we get the following resulting integral. And we can divide this integral up into two terms, the terms associated with the normal force density and the terms associated with the tangential force density. The terms that are associated with the normal force density are referred to as Maxwell forces in the literature. These are actually the dominant forces in most bearingless motors. The terms associated with the tangential force density are referred to as Lorentz forces, and in most systems they're insignificant compared to the Maxwell forces. However, for certain situations or for certain designs, the Lorentz forces can be the dominant physics. This is especially true of coreless designs where you don't have iron in the back, you don't have iron yokes. We'll talk more about that as we go. So we're going to take this one set of physics at a time. We're going to focus on the Maxwell forces first, and so I'm going to denote this by this variable fxr, and then second we'll go after the Lorentz forces and we'll denote it by fx phi, and then we'll add everything back up to get our final force expression. We're doing this because the math gets nasty. But before we go any further, let's quickly write out what the setup is for our y direction forces. And to get the y direction forces, we first go back and we look at our unit vectors again. So we dot our r hat vector with our y hat vector and our phi hat vector with our y hat vector. And then we go over here and we use that information to populate our integral. So instead of r hat dotted with x hat, we're doing r hat dotted with y hat, right? And instead of phi hat dotted with x hat, it's phi hat dotted with y hat. And so we can divide these up in the same manner that we have Lorentz and Maxwell forces. And we'll start with calculating our Maxwell force in the x direction. And let's first begin this by writing out what our normal field is in our air gap. So we're going to go back up to this list we created of fields in the normal and tangential directions and then plug them in to our stress component. So this time we're keeping track of the field that is created by both the torque and suspension winding. And so that's why you see, this field right here is from our permanent magnets, if it's a permanent magnet rotor. This field right here is from our torque winding in the radial direction. And then this field over here is from our suspension winding in the radial direction. And we're going to combine the torque winding and the magnetizing field into a single field that we'll denote as BM hat with an angle VM. So you see that these two fields are very similar. They just differ by the angle of the suspension, or the torque current space vector, which is phi. And so we'll lump this in into a single field for ease of solving these equations. And we can always decompose this back out to these two terms if needed. And similarly, we're going to keep track of our two fields in the tangential direction, one due to the suspension winding and the other due to the torque winding. So writing this out, so we've now set up our integral. We're integrating over the surface of the rotor, and here is our entire normal force density on the surface of the rotor in terms of our fields. And then we multiply it by the cosine of alpha because we're interested in only the x component, right? So that's this up here. And then we've got our surface integral, so times r d alpha. And that's what we're going to solve. So math gets complicated. We're going to simplify it right off the bat. It turns out that while this term here is capable of creating forces, we're going to assume it's zero. It actually turns out that it creates forces that are 2 to 3 orders of magnitude smaller than the first term. And so I suppose that you might get into a situation with some type of bearingless motor design where you might need to come back and revisit this term. But for the purposes of this lecture, we're going to treat this as zero. It ends up being that the forces you get are due to an interaction with the torque winding and the suspension winding. Oh, and I should clarify a few things here. So BM hat refers to the modified magnetizing field right here, right? BWS refers to the radial field due to the suspension winding, and BW tan refers to the field due to the torque winding. And we should clear this up. So this is BWS, and this should in fact be BWS tan. Tangential fields are always much smaller than the normal fields, or they are in machine designs with iron in the back in the stator and rotor. So the S's mean suspension, and if there's not an S indicated, it's due to the torque winding. All right, so we've eliminated this whole second term over here, and we'll instead focus our attention on the first term. And we're going to make the observation that to get non-zero integration results, we need to have an integrand that does not vary by the cosine of alpha or the sine of alpha. So remember, if you integrate over the cosine of alpha or the cosine of some integer number of alphas from 0 to 2 pi, you end up getting 0. And we're going to use the trigonometric identity that the cosine of u times the cosine of v is equal to the following. We'll just define this as a function f1. So we only care about terms in f1 squared that vary by the cosine of alpha. And the reason that we want the terms to go by the cosine of alpha, not an integer multiple, but cosine of alpha, is because we're going to multiply those terms by this cosine of alpha, and from this identity, we're going to be adding or subtracting alpha to it to cancel this alpha out. We've got this function here that we're going to multiply by the cosine of alpha. And we want the result to have no terms that vary by the cosine of alpha. So in order to make that happen, we want to track only the terms of this that are squared to vary by the cosine of alpha. I think it'll be easier to see as I do it. We're just starting to write the terms out. You can see that this very first term right here, when we evaluate the cosine squared using this, we're going to get cosine terms that either go by 2p alpha, and if you multiply a cosine of 2p alpha by the cosine of alpha, there's no way you get the alpha to disappear. Or we get a term that is the cosine of theta plus phi m with no alpha in it, but when you multiply that by the cosine of alpha still survives, and it won't make it to the integral. It'll become 0 if you integrate that over 2 pi. That means that this entire term doesn't matter. It doesn't survive the integral. Similarly, I've started writing out the next term here, and we can see that this term won't make it to the integral either. And finally, we get to the last term, and we see that we have a shot here. If we multiply these together, we get either p plus ps times alpha or p minus ps times alpha. And so keeping only the term that we care about and performing that multiplication, we get the following result. And by the same logic, this goes to 0, because p plus ps is always going to be greater than 1. But this right here, we can get this to equal 1. In fact, that is our condition. So we need the condition that our suspension pole pair number needs to be equal to our motor pole pair number plus or minus 1. We've just proved that. We said that at the beginning of the video, and now we've just proved that in order to create a Maxwell force, this needs to be true. This condition needs to be met. That's the only way that we are producing a net force on our rotor. So that is a very important result. And we can now go back and finish our Maxwell force calculation. We can plug this F1 squared value back in to our integral, multiplied by the cosine of alpha, and integrate. We now have an expression for the force that is on our shaft of our motor. And let's work with this a little bit. We can make some observations about what our current space vector must behave like. So we can see that to create a constant force, it's going to make sense that we define the angle of our current space vector to be a rotating component that rotates in the same direction as our direct axis of our motor. So it rotates in the same direction as our torque space vector. And then to have a phase angle, which we're calling phi SI. And then the second thing that we're going to do is we're going to plug in our expression for BWS hat. So we finally end up with this expression that I've put in the red box here, which is that our Maxwell force is equal to the volume of our rotor times this quantity that we've defined as sigma s on the right side, times 1 over our number of suspension pole pairs times our air gap length. Remember, delta is our air gap length, times the cosine of the difference in these angles, where phi SI we had just defined up here for our current space vector, and the phi m angle came from back here. And so we defined this phi s here to have the same form as this average of sigma f tan. So we're trying to create our scaling law to have the same form that we use for torque, which was up here. So in torque, expression was 2 times the volume of our rotor times the average of our shear stress. In this case, we've got the volume of our rotor times this quantity we've labeled as sigma s, and then times some additional terms. And the sigma s does not have the same physical meaning. It just is that we've clubbed these terms together. We've just lumped them together for our own convenience. Okay, so that's great. That's the Maxwell force. We can draw all kinds of fun analogies about how the Maxwell force scales with the machine dimensions in ways similar or different to the torque production. But you can see it scales pretty similarly. You increase your linear current loading, you're going to get more Maxwell force. You change the volume of your rotor, it's going to change in the same way as torque changes. What is different is that your air gap length is going to heavily influence how much Maxwell force you get. You want to have a very small air gap length. And interestingly, larger numbers of suspension poles are going to decrease your Maxwell forces. Let's now take on Lorentz forces. So we're going to go and do this term now. So we've set up our integral for the Lorentz forces the same way we did for the Maxwell forces. In this case, we're using sigma F tan instead of our normal force density. And here you can see we've got our normal fields, like we've been talking about, where our magnetizing field and our torque winding field are lumped into this term. And then over here we've got our tangential fields. The first term is our torque tangential field, or our torque winding tangential field, and then our suspension winding tangential field. And so what we're going to do is we're going to use the same argument as before, that we want to work with our integrand here and only consider, we'll multiply our sines and cosines through, but then only consider terms that do not have a sine or a cosine of alpha. And we'll use the following trigonometric identities to get there. And so if we do this, we pull our integrand out, we can start to work with it. And we get this expression for our Lorentz force. Let's work with a little bit to get into a more convenient form. First, we'll start by plugging in our expression for BWS. So you see that we can rearrange terms a little bit to get this more analogous to get this in a form that's closer to what our Maxwell forces were. And the reason that we're doing that is that we are now going to combine the Lorentz and Maxwell forces, and we want to write this in as convenient of a form as possible. We'll say that our total Fx is equal to our Maxwell plus our Lorentz forces. And we get this form that I've underlined here in red. In this form, this corresponds to our Maxwell force term, and these correspond to our Lorentz forces. Now we can work with this a little bit to simplify it, because I'm going to show you that this term right here doesn't matter, it's negligible. So we can see that by comparing this term to this term right here most easily. If we assume that the cosine in both terms is 1, that means that they're operated at an angle that gives them the largest value possible. All we need to compare is this quantity right here against this quantity. And so if we load these with practical values and evaluate it, we're comparing a number that is approximately 0.01 to a number that's approximately 1. So this term over here in normal machines is going to be 2 orders of magnitude smaller than this term, and that means that we can safely neglect it, at least in standard cases. The big caveat with bearingless motors is that they're oftentimes used in very unconventional configurations, and sometimes you may need to go back and relook at these physics to see if they were important, to see if they mattered for your specific use case. You can go back and do the same derivation in the y direction. And if you do that and neglect the same terms that we neglected here, you can write your force expressions in the following form. And I'll put the almost equal sign, but we're going to take this as the truth. that this is exactly what they're equal to. And so along the way, we came up with expressions for all these subcomponents in here. The main thing to note is the sigma s, we said was bm hat times as hat over 2, where bm hat is the result of our magnetizing field added to our torque winding field, or the armature reaction field. And then the second thing to note is that phi m is the location of the resulting B delta plus BW. And this assumed that we had a suspension current space vector like this. And if for convenience sake we copy our torque sizing law down here, we can make a set of conclusions. The first observation is that our torque and suspension force capabilities, or ratings, scale in a similar manner. They both scale by the volume of the rotor and by the magnetic and electric loading. The second observation is that machines with PS equals P plus 1 pole pairs will have larger suspension force ratings. The caveat to this is that notice that your Maxwell forces will actually decrease as you increase the number of suspension pole pairs. The third observation is that in order to create constant forces, constant direction, constant magnitude forces, we can see from this expression that we need to have suspension currents that are at the synchronous frequency. So that means that our suspension and our motor currents will be at the same frequency in order to create constant forces. This is despite the fact that our suspension winding has a different number of pole pairs as our motor winding. So this concludes this video. In summary, we went back to our expressions for the fields in the air gap of our machine and our expression for the forces that act on the rotor in the form of the Maxwell stress tensor. And we use these to derive the torque first that acts on our rotor and produce the familiar machine scaling law. And second, to derive the forces that act on our rotor when we excite the suspension windings with three-phase currents. We then constructed final force and torque expressions and compared them to discuss how the machine scales and draw conclusions about the proper selection of the number of pole pairs for the suspension operation and the frequencies that we expect our suspension currents to be at.